So, in your notes yesterday, I gave you a few formulas in the context of finding the limit version of these problems. And we are going to steer clear of the limit version for a second so that you can kind of get more comfortable before we jump into it. But one of the things that I gave you yesterday as part of the formula was I told you what delta x was. And the reason that we're going to use that right now is because delta x is actually the width of the interval. And yesterday the width of the interval was easy because your interval was from 0 to 1. So if you have 2 subintervals, then it's just half, right, from 0 to 1. If you have 3 subintervals, it was a third. If you have 4, that was easy. But if you look at these intervals, they're a little different. They're less easy to work with. So I'm just going to remind you of that formula. It was b minus a divided by n. And the b is the upper bound of your interval. The a is the lower bound of your interval. And the n is the number of rectangles you're drawing or the number of subintervals that you have. So how you're breaking it up. So for this one, the first one, it says that our interval is from 1 to 3 and we're breaking it up into 6 pieces. So we're going to say that the width of our intervals is 3 minus 1 divided by 6. And so how wide is each of our intervals going to be? Yeah, 1/3. So that's 2 over 6, which is 1/3. So it says that we are using left endpoints to draw our rectangles. So I'm going to start at 1. I know I'm going to do thirds with this, so I'm going to go ahead and break them up into thirds as best I can already. So my left endpoint comes from the curve, and then I go over a third, and that is my first rectangle. I'll go ahead and make it filled in so you guys can see it. Is that rectangle an overestimate or an underestimate? Overestimate. We have that little bit of space above. Okay. Our next rectangle, we're going to use the left corner. That's pretty good. I feel like that was on the way there. We're going to use the left endpoint again. So I'm going up, 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 but using the left side. Okay, so do we feel comfortable with the idea of left endpoints?
What's the difference?
In a second, I will draw a couple right endpoints on the same picture so you can see the difference.
Okay.
Typically, a left endpoint will give like an overestimate or an underestimate, and then the right endpoint will do the opposite. So depending on the picture, one will do one thing, the other. Because I think when we did the video last night, the left was the one that was the underestimate. But right now, this
Does that just depend on the function?
yeah, it depends on if it's concave up or concave down. So that means that the height is actually coming from the y-coordinate of the curve. Did you guys catch that in the video?
Mm-hmm.
The height of the rectangle comes from the y-coordinate of the curve. Okay, so all of those were underestimates. We're just drawing that picture. Do not draw this next part. I'm just going to show you the difference between the left endpoint and the right endpoint for this picture. So for the first rectangle, if we were to have done a right endpoint, then the rectangle would have stopped right there. You guys see that? So here's the right endpoint for the same rectangle. So the rectangle has the same width, but if I find the top of the rectangle based on the right side touching the curve, it actually makes the rectangle shorter. It makes it an underestimate instead of an overestimate. And then if I was to do the next one, it would put it right there. So do you see the difference? Does that make sense? Okay. So, and that's why we're just gonna, these are called Riemann sums. Sometimes they're gonna ask for the left endpoint, sometimes they're going to ask for the right endpoint, sometimes they're going to ask for the midpoints. Depends on the problem. It's just a way of approximating an answer that we will find an exact version of later. That's all it is. Okay. All right, so for number 2, we're going to do the right endpoints for this one. Our intervals from 1 to 4, and we're going to do 4 subintervals. So we're going to do 4 minus 1 divided by 4. So how wide are the intervals this time? 3/4. Okay, so starting at 1. Yeah. Okay, so there's 3/4 right there. There's the next 3/4. There's the next 3/4.
What is the purpose of drawing these squares again?
You are approximating the area under the curve, and we're going to do it using rectangles because we know how to find the area of a rectangle. It's length times width. So we're just dividing it up into different rectangles so that we can find the area underneath the curve.
Okay.
So if I go up here,
I don't understand when you're supposed to stop the rectangle.
I second that.
so this is 1, right? So what I did is I took the area from 1 to 2 and I divided it in half and then divided it in half again, so I would have 4ths.
No, I mean like at the top.
Oh, at the top. So this one is right endpoints, which means I'm taking the end of my 3/4 and I'm drawing it up here and I'm using the right endpoint on the curve. When you're doing left endpoints, you use the left side of the rectangle and you stop it where it intersects the curve.
What would that look like if we were using left on this one?
On this one, your rectangle would have stopped right there.
Okay.
Does that make sense? Yeah.
Why do you start at 1 and not 0?
You start at 1 because the interval starts at 1.
Oh, okay.
Mm-hmm. Good questions. Okay, so this one I'm going to draw it just up here, see where it intersects. So with this one, because the curve kind of goes back and forth, we can see that we have an overestimate for the first rectangle, but the second rectangle is an underestimate.
Why are we drawing these big rectangles again?
So when you do these ones, remember in the video I said you can have any number of rectangles, right? The more rectangles you have, the more accurate your answer is. So if you had the patience to draw 50 rectangles, your answer would be so much better than drawing 4. But the balance is who wants to draw 50 rectangles.
Right.
So this is where you're kind of trying to figure out how much time do I want to waste on this problem versus how accurate of an answer do I want.
Okay.
So you often find people drawing a smaller number of rectangles just knowing that their answer is not as accurate as it would have been if we drew a bunch more. And then the idea of the limit is we're saying if we draw infinitely many rectangles, then our answer should be perfect. Because we drew like a million trillion rectangles, that would be a really, really accurate answer.
So we can just make, we could have done like 20 for one.
You could, but it would be a pain in the butt, yeah.
Right.
Yeah. So typically when these problems ask you to do this, they ask you to do somewhere between like 3 and 7. They wouldn't ask much more than that because it gets to be really tedious.
Yeah.
Okay. All right. The next one says our interval is from 2 to 4. And we have 3 subintervals, so we're going to do 4 minus 2 divided by 3. So what is the width this time?
2/3.
2/3. Okay, so be careful of this one though because these are midpoints. So to find the height of our rectangle, we have to look at the middle of our interval. Okay, so I'm going to start at 2. I'm going to draw my thirds in. I know that this one is what makes my rectangle, and this one is what makes my rectangle, but the height actually comes from the middle. Does that make sense? We're not using left endpoints. I'm not looking at where the left side connects with the curve. I am not looking at where the right side connects with the curve. I'm looking at where the middle connects with the curve.
So why did you make those lines bigger?
Because so that I would know what the ends of my rectangle are.
Okay.
So this is what's going to make my height right here. There's my height, but here's my rectangle. See how I got the height right from the middle? Okay. And here I'm going to get, this one's nice because it's already drawn. We're going to get our height right from the middle. we'll get our height right from the middle. What's the benefit of using midpoints as opposed to left endpoints or right endpoints?
Over underestimates.
Yeah, they're not over and under as much. They're kind of like a compromise. So the middle of each rectangle is where you see it connect with the curve. So the middle of the rectangle gave me my height. And again, remember the height is the y coordinate of the curve.
Say that one more time.
The height is the y coordinate of the curve. So if I wanted to know the height of this first rectangle, I would take 2 1/3 and I would plug it into the function to find that y coordinate.
Okay.
If I wanted to know the height of this rectangle right here, I would plug 3 into the function.
Okay.
If I wanted the height of this one, I would have to plug in 3 2/3 into the function to find the height.
And you wouldn't do like 4 because it's not a midpoint.
I wouldn't do 4 because it's not a midpoint, and 4 does not connect with the curve. So I'm doing the point on the curve to figure out my height. All right. We feeling okay with that? Drawing that? Okay. Now, they're not going to ask you to draw it every time. They're basically going to say, you figure out how wide it should be, and then you have to know what x value to plug into the curve to find the y value that you want. So we're going to draw a bunch of them today so we can start to make that connection, so we can visualize it. But once we get to the point where we understand it, then we won't be drawing the pictures anymore. We'll just make sure we're using the left side of the interval or the right side of the interval or the middle of the interval. Okay? All right, so what we're going to do now is we're going to do this one right here. So we're going to find the area under the cos curve on the interval from 0 to pi halves. And we're going to find the area using midpoints and 4 subintervals, and then after that we're going to go to that dreaded limit formula and see if we can write out just the general area if we were to do infinitely many rectangles. Okay? So what should I start with?
Delta x.
Yep. So delta x is, here's our interval, pi halves minus 0 over 4. It would be infinity if we were doing like the limit version. That's when we would say infinitely many. So over 4. So the width of each of our rectangles would be pi halves divided by 4, pi eighths, yeah. Okay. So, and remember, when I say under the curve, I really mean between the curve and the x-axis. So we're not looking down here at all. We're only looking at this part right here. That's what we're looking at, okay? So I'm going to go ahead and make this into fourths. Okay. And it said they want us to use midpoints. So I'm going to label my fourths, but then I know that when I go back and do it, I'm actually not even going to use those. So this is 1/4 of pi halves would be 1/8. 2/8 is 1/4. 3/8, and then 4/8. So I divided it up into 4 equal intervals, right? 1/8, 2/8, 3/8, 4/8. You see that? Okay. And then we're using the midpoint to draw the rectangle. So from the middle, that's how I'm drawing my rectangle. What's the middle of 0 and 1/8? The middle of 0 and 1/8? 1/16. So the area of our first rectangle, I'm going to say m sub 4, so that means I'm finding the area using midpoints and 4 subintervals. My first area would be a width of, what's my width?
An 8.
Yeah, pi eighths. And then how would I find my height?
You plug it in.
You plug it into the function. So the thing that we're plugging into the function is the middle, which is,
Cos of pi 16.
yeah, pi 16. So we're plugging it into the function, so we're going to say cos of pi over 16. So this is our width. This is our height. So the reason yesterday that we had something squared every time is because we were plugging it into the function x squared. This time we're not going to have something squared, we're going to have cos of something to find each of our heights. Okay, so plus, let's go ahead and figure out the next rectangle. So again, here's our middle. We'll find where the middle cuts into the curve. That's going to be the height. So the middle of the last one was 1/16. That makes this 2/16, and the new middle is 3/16. Okay? So the width of the interval is pi 8ths. So the width of the rectangle is pi 8ths. The height of the rectangle is cos of 3 pi 16ths. There's our second rectangle. I was just counting, so this is 1/16, 2/16, which is 1/8. 3/16 would be the next middle. Okay. So to do these, sometimes we have to be relatively comfortable with fractions, especially on the midpoint problems. Okay, so we're going to draw the midpoint of the next one. So a width of a rectangle is pi 8ths, and then cos of 5 pi 16ths. That's the height. Okay. And then our fourth rectangle has a width of pi 8ths and a height of 7 pi 16ths. Okay. So do you guys remember the point of the limit version of this?
Is it with the I in it?
It's the one with the I in it. It has two purposes. One is so we can do infinitely many rectangles. So obviously that's kind of beneficial. The second part of it is so you don't have to write all this stuff expanded out like this. It's like a shorthand way of writing that. That's why.
Of n to the infinity delta x at z.
And then it has the summation. Summation means you're adding things repeatedly. So when we do this, we're adding a bunch of different areas together. The nice thing about the limit notation is you can express the problem without writing all the plus and figuring everything out. Yeah. Okay. We said, I said in the video there's a way to kind of shorthand this. Do you guys remember how we could shorthand it before we plug it in our calculator?
1/8 times everything.
Yeah, the GCF would be the pi 8ths. That's our width. So the width, and this only works if you have the same interval for each of your widths, which is great when you have a picture of a graph. It's not as great when you have a table. If you have a table and they didn't give you equal widths, then you have to do it by hand one at a time. But this one, we had a graph and we made it so the widths were equal. So now we're just going to say cos of pi over 16 plus cos of 3 pi over 16 plus cos of 5 pi over 16 plus cos of 7 pi over 16. There is a faster way, but we're not there yet. So we are going to do this way. Anytime they are asking you about Riemann sums, that's what we're doing. Anytime we have less than infinitely many rectangles, and they say like do 4 rectangles or do 3 or whatever, these are all called Riemann sums. This is the most simple way to do a Riemann sum, is to do it like this. Okay, there's no simpler way to do it. All right, so in our calculator, make sure you're in radians. It would be tragic if you weren't. And then we are going to type in this whole mess. And you are not allowed to say, Miss Rice, I'm just going to sit back and let you do it because you're my calculator. I am not your calculator. They used to say that last year and then they couldn't, they'd get them wrong on the test. You gotta practice typing it yourself so that you get good at typing it so you can get it right on the test. Alright, so I had my pi 8s. Make sure you're getting all your parentheses in the right place. Where's your calculators, guys? And don't you dare say Miss Rice, you're my calculator. There's some in the floor still. Will you grab one for Leonzo too?
What's our thing? You don't want this
Yep, there you go. Alright. Is that what we're getting? Okay. And the actual answer is 1. So that's very stinking close. Yeah. So the midpoint did a good job this time. Alright, so I'm going to say that the area underneath the curve is approximately 1.00. That's not a 00. 1.006. Okay.
What is this? What are we approximating?
The area underneath the curve from 0 to pi halves. All right. So what we're going to do is we're going to figure out the different pieces to this so that we can write it down in the limit notation. Okay? All right. So let's go ahead and do the x sub I. Now for this one, instead of using our delta x as pi over 8, we're going to say that we're going to use the n here, right? Because when you do the limit notation, you're saying infinitely many rectangles. So we're going to say that it's pi halves minus 0 divided by n. And if you have pi halves minus 0 divided by n, how would you write that instead of pi over 8? It'd be pi over 2n. And if you divide by 2 and then also divide by n, like here when we divide by 2 and we also divide by 4, that's like dividing by 8. If you want to think of that as a 4 over 1, you can keep it, change it, flip it. So we could say pi over 2 divided by 8 over 1. And then you can flip that up, that's 1/8. Or sorry, not divide by 8, divide by 4. And that's how we got pi over 8. So if we did it with this one, we could say pi over 2 divided by n over 1. And we could flip up the n over 1 to have 1 over n. And that's how we get pi over 2n. Okay. So it works the same. All right, so that's that part. The xi comes from you saying that this is the width of your interval. So if you guys noticed, we said that we were starting at 0. And the width of our interval was 1/8. And then we start at 1/8, then the width of our next interval goes to 1/4. And then we have 1/8, the next width goes to 3/8. And then the last one goes to 4/8, which is the 1/2. Okay? So the way that we're writing this is here we would have said, for our original problem, we would have said pi 8 multiplied by I is just whatever term you're on. And we would have said plus 0 because the lower bound was 0. For our limit formula, we're going to say pi over 2n times I plus 0. And this doesn't make as much sense today as it will make once we start to take the pictures away and figure out what numbers we're plugging in for cos or whatever function we have using left and right endpoints. So for today, just kind of try to track along with us. It will make more sense as we go on. Okay? All right, so we have our delta x. We have this part right here would help us figure out what numbers we're actually plugging into the function. Okay? All right, so we're going to say the limit as n goes to infinity. So we're saying infinitely many rectangles because we're actually getting an accurate answer this time. And the width of our interval is pi over 2n. So that's the part where we took this and we pulled it out in the front. You guys see that? Okay, so our width. times, and then this is the part where we do the summation. Because if you look, the width of our interval was pulled out. The heights of each of our rectangles is what we had to add repeatedly. You guys see that? Okay. So we're going to say I equals 1 to n.
Is I always
Yes. You always start with 1. Yes.
When I look at the formula on our notes, it says delta x. So why do we put pi over 2n?
Because that was our delta x
For this sort of...
for this specific problem.
Okay.
Okay. And then the next part it said in your notes is f of xi.
And you plug it in.
And so that's cos, because our f of x was cos of x.
Okay.
And the thing that we plug into cos is pi over 2ni plus 0.
What is the I plus 0?
So the I is saying we have the first interval, then the second, then the third, then the fourth. The plus 0 is saying that all of these little answers, all these numbers were based off of us starting at 0. Okay. So right now it's going to feel a little confusing. The more examples we do, the more sense it will make. I think that this specific part of it won't make as much. Today it will be maybe you kind of memorize the different pieces. Once we pull away the pictures and start doing more problems with just functions, I think it will make a lot more sense. All right, go ahead and flip that over. We're going to work at the back of the page. All right, so we have a much more complicated function. You guys see it? And we're doing from -1 to 2. What do you guys notice is different about this picture? It's going down. So remember when it says the area underneath the curve, it's still, the graph is going up. The area underneath the curve still means between the curve and the x-axis. So the area underneath the curve is actually this part right here, which I would kind of think that's like above the curve, but no, it's still called the area underneath the curve. It just means between the curve and the x-axis. Okay? So that's what we mean by area under the curve for this one. We are using 6 sub-intervals. So first thing, we're going to find our delta x. What is our delta x?
2 minus plus 1.
Yeah, 2 minus -1, which is 2 plus 1. Divided by
6.
6. Okay. So we have 3 divided by 6, 1/2. Okay. So we're going to do this problem twice. We're going to use right endpoints, and then we're going to do it again using left endpoints. Okay? So I'm going to say R sub 6 for 6 subintervals. Each of our intervals is a width of 1/2. Okay, so for the first set of answers, we are going to use the right endpoints. So I'm taking the right side of my interval, and I'm drawing a line down to where it connects with the curve, and that is the height of that rectangle. Okay? So that's 1/2 times the function. Are we okay with saying f of x instead of writing all of these out each time? Okay. So the function evaluated at what x coordinate would give me the height of that rectangle? You're close. It's the right side. -0.5. -1 is over here.
Okay.
We're using right endpoint, so it would be -0.5. So I'm going to say 1/2 times f of -0.5. So there's our width, there's our height. Plus, all right, right endpoints. There's my second one. So the second one has a width of 1/2. And the height comes from when you plug in what to the function? 0. Yep, good job. So 1/2 times f of 0 plus the third one has a width of 1/2 and a height from plugging in 1/2. So a width of 1/2 and then plug in 0.5. The next one has a width of 1/2 and a height that comes from plugging in 1. A width of 1/2, a height that comes from plugging in 1.5. And then our last one is a width of 1/2 and a height that comes from plugging in 2. Okay. So how do we shorthand this?
1/2. All the F's.
Yeah. So f of negative 0.5 plus f of 0 plus f of 0.5 plus f of 1 plus f of 1.5 plus f of 2. Is anyone else concerned about having to plug it into that function? How obnoxious that's going to be? I'm going to show you a calculator trick. Are you ready? Okay, so go ahead and finish writing that out, and then I'll show you the calculator trick. Yeah?
Why can't we just write it like the simpler way from the start?
You can.
You can?
Yeah. I'm showing you guys this way repeatedly so that when I start to only write it like this, you'll be like, oh, I remember where that comes from because she made us write it 50 million times first. All right. So, grab your calculator. Go ahead and hit y equals and plug this into y equals x to the third minus 3x squared plus 2x minus 1. We are not going to use the table because if you use the table, you would have had to write down all the y coordinates separately. And if they're messy decimals, then you'd have to round them to write them down. And as we know in calculus, you don't round till the end. So we're plugging this in here, and then we're going to quit. We're going to get out of that screen. So go back to your normal screen. Okay. And we still have to type that part where we have the width of each of our rectangles is 1/2. So go ahead and type in your 1/2 in your parentheses. And so this is where we're going to type in the part where we say f of negative 1/2, f of 0, f of 1, all of that. The way that you do the f of in your calculator is you hit the vars button. See the vars right there? Hit vars. Go over to y vars. Press enter. And now it's saying which y vars you want to use. You want to use the thing you plugged into y1. So press enter. So this is the equivalent of f of. And you're going to put parentheses negative 0.5.
Do that vars thing again, please.
Plus, let's go ahead and do the next one. Bars. Go over to y vars. Enter, enter. F of 0 plus vars over, enter, enter, 0.5. And make sure you do the parentheses of 0.5 of 1. Vars of 1. Vars of 1.5. Vars of 2. Remember, I am not your calculator. You should be practicing this yourself. Okay? So instead of our calculator saying f of all these things, it's going to say y1 of negative 0.5, y1 of 0, y1 of 0.5, and that is our calculator's way of saying we are taking that function and we're plugging in all those values. Okay. Aren't you glad we're using a calculator though?
Yes.
Whew. Thank goodness. Why is the area negative?
It's below the x-axis.
Yeah, it's below the x-axis. Okay. Aren't you guys excited to do this whole thing again with left endpoints?
I'm dead. What?
Okay, so because we just did all that work with right endpoints, the left endpoints are actually going to be very easy. Don't clear your screen, just set your calculator off to the side. We're going to go ahead and we're going to adjust our pictures for this. So if you want to grab a pen so that you can see the difference, or if you want to write over it in pencil and get very confused, you can do that. So this time, my rectangle, instead of starting at the left endpoint, it's going to start at the, or sorry, instead of starting at the right endpoint, it's going to start at the left endpoint. Do you guys see what that does to your rectangle?
Yeah.
Makes it so much bigger. Everyone see that? Okay. Like Chrissy pointed out, we can go ahead and do the easier notation, right? So we're going to, instead of showing all of these different ones, we're going to start off with the shorthand. Are you guys okay with that?
Yeah.
Okay. So I'm going to say left endpoints using 6. I'm going to say my overall width is going to be 1/2 every single time. What am I plugging in to get the height of my rectangle this time? I'm plugging in -1. That's the very left side. So f of -1. Okay. For my next rectangle, do you see how the right endpoint of the first one just became my left endpoint of the second one?
Mm-hmm.
Ooh. Okay. So what are we plugging in to get the area of this rectangle? F of -0.5. Okay. The next one is going to be the f of 0. The next one is going to be the f of 0.5. Do you guys see how similar this is to what we just plugged in? But here's the nice thing. That means you're not going to have to really plug it in again. So instead of starting at -0.5 and going all the way to 2,
Yeah.
we're going to start at -1 and go all the way to 1.5. So what is the only difference between these two? The 2 at the end and the -1 at the beginning. Do you guys see that? Okay, so here's what we're going to do in our calculator. We're going to hit second enter so we pull all that stuff up again. We're going to go in here, we're going to delete the 2. Delete the 2. And to insert, do you guys see the INS? We're going to hit second insert and type in a -1. So I took out the 2 and I replaced it with a -1 because that was the only difference in the 2 problems. Okay?
Whoa.
It makes a much different answer though, doesn't it? Yeah. Why did the answer get so different? It was so much more negative this time. Yeah, we have 2 of our rectangles are much more negative than they were before. They have a much bigger negative area. How I plugged the new numbers in. So I did second enter and it pulled everything up. You could also like go up and highlight it and press enter. And then what I did is I deleted the number in that last set of parentheses. And I wanted to plug in a -1, so when it's blinking, if it's blinking on the thing, you want to plug something in right before that. So it's blinking on the right parenthesis, and I want to plug something in before the right parenthesis. Then I can hit second delete, which is insert, and then it will let me insert anything in front of that parenthesis. So wherever it's blinking, it will let you insert right before that. So I just took off, that's all I did. I took off the 2 at the end, I put a -1 at the end instead, and I got my answer. All right, we're going to do the limit notation.
I didn't either.
If you didn't get it, it might just be how you plugged, how you fixed it, so I can come over and I can help those of you individually who had a hard time with that. Okay, so just leave your calculator open, leave it on so that I can come back and look at it. Okay, we're going to do the limit notation. So we're going to figure out what our delta x would have been if we didn't know how many intervals we had. So if we do delta x and we do not know that we have 6 subintervals, then what we would have done is we would have said 2 minus negative 1 divided by n. That's what we would have said. Okay? So our delta x would have been 3 over n. Alright? I'm going to go up here. I think the xi for this problem might make a little bit more sense to you guys. So the xi comes from when you take this number right here. Remember, it was delta x times I plus the lower bound. So this is 1/2 times I plus, what was the lower bound? The lower end of the interval. So plus negative 1. So what this notation means is start your numbers at negative 1 and add 1/2. So negative 1, negative 0.5, 0, 0.5, 1, 1.52. That's what that notation is telling you to do. It's telling you where the edges of your rectangles are. Okay? So we're going to say our delta x is 3 over n. Our xi is going to be 3 over n times I with a minus 1 on the end. Or you can write plus negative 1, it doesn't matter. Okay, so we have the limit as n goes to infinity of the width of our rectangle, because that's the thing that goes out in front of the parentheses, right? That number only happens one time. And the width of our rectangle in this specific problem was 1/2. But in general, if we had as many subintervals as we wanted, it would be 3 over n. So there's the width of our rectangle right there. And then the summation part is the part where we have all the different heights of the rectangles. And they're all different there, and we add them all up. So we're using the summation because we're adding up all the different heights. So we have, you start off where I is 1, and you go all the way to however many rectangles you have. And then we have the function being evaluated at that number. So we did that, right? We had the function evaluated at negative 1. The function evaluated at negative 0.5. The function evaluated at 0. So we're going to say the function evaluated at 3 over ni minus 1.
Why couldn't you just put like negative 6.9 plus 12?
That's the answer.
Right.
That's not what we plugged in. So this is a shorthand for writing this.
Okay.
This is not saying what the answer is, it's just a shorthand for writing what we plugged into the calculator.
What is the 3 and I minus 1?
That's I start at negative 1, and this is the pattern for how wide each of my intervals is.
To infinite.
So for the problem we just did, it was 1/2 I minus 1. Because you started at minus 1 and then you added a half each time. Okay. So I'm going to go ahead and I'm going to write this out one more time, but instead of saying f of something, I'm going to use my actual function. I equals 1 to n, and my function was x to the third, so that's 3 over ni minus 1 to the third, minus 3 times 3 over ni minus 1 to the second, plus 2 times 3 over ni minus 1, minus 1. So what I did is I took the stuff that I said we plugged into the function, and I literally plugged it into the function. You do have to do that. Yeah. Okay. It is okay if you don't totally grasp it today. You might have to kind of memorize these steps for today. Once we do it over time, I think it will start to make more sense. Okay, so, and this is not the only day we're going to look at that. I will continue to explain it as though you haven't seen it before. Okay? All right. We've looked at these where we can where we have a function to plug something into, and we have a graph, and we can make the intervals the same width every single time. Now we want to look at a problem that's a table where the intervals are different widths, and so we can't use our shortcuts. Okay? So when we look at this one, it says use right Riemann Sums. So that's what we were doing. It's saying use a rectangle and have it be the right side gives you the height, and 4 subintervals to find the area under the curve. Okay, so that means we're going to divide this up into 4 rectangles. So you can see here's one rectangle right there. So from this one to this one, here's the second rectangle from this one to this one. Here's the third rectangle from that one to that one. And then here's the fourth one from that one to that one. So in between here makes a rectangle. In between here makes a rectangle. In between here makes a rectangle. In between here makes a rectangle.
Yeah, your brackets.
Did the brackets kill you? Let me erase those. So I don't know how you want me to draw it to make it make sense. But basically the rectangle happens in between the points. I got you. Okay, so here's a rectangle right here. Okay, so the width of this rectangle goes from 0 to 4. And the height of the rectangle, if we were using a left endpoint, is 7. If we were using a right endpoint, is 13. Okay? So it says use the right endpoint, so we're going to say width is 4. The height is the right side, which is 13. Okay? For the next rectangle, we're using these ones. From 4 to 6, what's the width from 4 to 6? 2. What's the right endpoint height? 18.
What's the width from 4? How did you get to again?
Because from 4 to 6 is a length of 2. Alright, here's our next one. From 6 to 10 is 4. The height would be 23. Alright, and then the last one is 3, and the height is 27. Okay, so we're going to go ahead and type those in our calculator. Now, notice this time we can't take out a GCF because there isn't one. All the widths were a little different. Now, if you want to find the units for the problem, you have to consider the units that you plugged in. So when we did from 0 to 4, that number 4 represented minutes. Does that make sense? So I'm going to say 4 minutes. I'm just going to write down just the first one down here so I can see how the units interact with each other. Okay? And then from the 7 to the 13, that was gallons per minute. So that means that the 13 was gallons per minute. Okay, so when I multiply minutes times gallons per minute, what do I get? Wait. I have a minute on top and a minute on bottom. They cancel. It's just gallons. It's just gallons. So let me write this a different way. I had 4 minutes times 13 gallons per minute. And my minutes cancel. So it is not the slope. This is not derivatives. Okay? So that means that from a time of 0 to a time of 13, approximately 261 gallons are pumped into the tank. Okay? So what does this represent? That's the sentence we're going to write. We need to be careful to write a good sentence because you guys on the test, we had a hard time writing sentences to make sure we actually understood what things meant. So what this means is for time is 0 to 13 minutes, 261 gallons of water was pumped into the tank. Okay? So anytime you need to check your units, that's how you can do it. You can take the units from one of the rectangles and multiply them together. That will give you your units. Okay?